So this is the first part of the chapter 6.5, and we'll talk about least squares method. And this first part, I will just introduce the method, derive some important formulas, and in the other parts, we actually look at a couple of examples. But first, let's look what is the least square methods and when do we want to use it. And most common way to apply this method is when we are trying to solve the data-driven linear system of matrix equations, matrix A times vector X is equal to B. So we're trying here to solve this A system for vector X. And because we are dealing with the data, sometimes we just cannot find a solution. The solution does not exist, system is inconsistent, and mostly it's just a result of the noise. And in the beginning of this chapter 6, you saw the description of the GPS positioning system when the data from the satellites are integrated into the matrix, and we need to solve this matrix equation to find the position of the device. And sometimes there is just no solution. So what can you do? You cannot just say to the client that, there is no solutions, there is no coordinates for you. You need to find a position. Maybe imprecise, maybe there is some error involved, but having imprecise coordinates is better than none at all. So you have to find what's called an approximate solution. Let's see how we can find it. And again, let's introduce the terminology of the vector space here because it's easier to derive things. So we are telling here that we are solving this equation AX is equal to B. So we're looking for solution, and this solution should be, precise solution should be in the column space of matrix A, and it's in green area here. But our solution does not exist, which means that right-hand side, vector B is actually does not belong to a column space. It's somewhere outside. How we can find this approximate solution? We just need to find some kind of vector B, some kind of right-hand side, which is located inside our column space, which has a solution. And there's plenty of points like this. For example, AX1, it is a solution of our equation. AX2, another solution of our equations, but they are kind of far away from our vector B. There is a vector which is close to our original right-hand side B. And of course, best approximation theorem offers us a vector like this. It's just telling us that if we would like to find the point closest to our vector B, that would be our projection, and specifically projection of our vector B on the column space A. All we need to do is replace our right-hand side with this projection vector, and we should be done here. All we need to do then is find this vector X bar, which transformed by matrix A into this B head of projection vector. Easy enough, but it's actually a rather complicated solution, so let's go through some derivation. So we know that our B head over here belong to the column space. It's a solution. We're looking for this actually, which means that now finally the matrix equations AX hat is equal to B hat is actually consistent. We can solve it. And even more, by orthogonal decomposition theorem, our difference between our vector and its projection, B minus B hat, is actually happen to be orthogonal to the column space. Which means that this difference, B minus A times X hat, and what I did here is just replace our B hat with left-hand side of the matrix equation. And this vector, which indicated here in blue, is actually orthogonal to each column of matrix A. Okay, let's take one of this column. Let's denote it AJ. And since it's orthogonal, we know that the dot product of this column AJ by the orthogonal vector B minus AX hat should be equal 0. It's just definition of orthogonality. We also can write it down, this dot product, as the product of transposed column AJ and B minus AX hat. It's just a different, just a linear combination. It's just different. It's just definition of the dot product. So not a big deal. So what's happened now? We actually know that our transposed column AJT is a row of transposed matrix A. So we can write it down, our equations right here for the whole matrix, for transposed matrix A. Okay, so we modify now equations. So let's now go ahead and use the matrix properties to factor in the transposed matrix A. Okay, so we multiply our transposed matrix by the first term B, multiply a transposed matrix on the second term AX hat, and it still equals 0. So now let's reorganize our term and keep everything which has X hat in the left side and everything which doesn't to the right hand side. So we just reorganizing the term here. So we have a new equation here, and it's a very, very interesting equation and very useful here. It's called a system and normal equations. And although it looks a little bit clunkier, it's actually easier to solve. And theorem 13 telling us that so that least series of least square solutions, AX is equal B, is actually coincides with the solution of this normal equations. And most of the time, when we're trying to find the approximate solution using a least square, we actually will solve this system of normal equation rather than using the projection formula. And in the next couple of mini lectures, I'll walk you through the couple of examples of solving such system of equations.